Hello, my name is Jason JERALD. I'm the CEO of Next Gen Interactions, and today I'm going to talk about human-centered design with physical props. That is, integrating physicality into virtual reality simulations. I've been working with virtual reality, building systems and applications for a bit over 20 years now. Perhaps I'm most well known for my book, the VR book, Human-Centered Design for Virtual Reality. I'll be talking about some of those elements today specifically applied to the physical aspects of virtual reality and how we interact physically with things. And if you want to learn more about human-centered design in general for virtual reality, check out the book at thevrbook.net. Okay, there's a whole lot that goes into a virtual reality or an augmented reality system. Essentially, at a very high level, we need to be able to track the user in some way to know where they're looking and such. And then the software application essentially simulates the world. And then we render, we draw visuals, we output audio, we provide haptic feedback, haptic being a way to convey the physical touch. And then we display that on the hardware back to the user. Now, the important part here is the user. Without the user in a virtual reality system, there is no virtual reality. And so at Next Gen Interactions, we take the approach of really thinking about, okay, how is this going to work with the human from that human-centric approach instead of a technology-centric approach? Obviously, there's a lot of technology and engineering that goes into that, but it's designed around the human instead of the human being designed around the technology. And so it starts with perception. Here's listed the primary senses as humans have, sight and hearing. Obviously, those things are pretty important, and we're doing this pretty well as an industry in virtual reality. We can have high-quality visuals. The audio is rendered in pretty well. Then there's something else called proprioception that we sort of take for granted in the real world, but it becomes very important, and when we need to understand that in virtual reality. That's where our body parts are located. And so, for example, if I close my eyes and reach out, I can easily touch my nose, right? I pretty much know where that is, even though I don't need to think about it. And it's also where are your hands located and such. So if I want to reach out to the side of me, maybe I can grab something without actually having to look at it. And if that's out of balance with what I'm seeing versus where I kind of feel where my body parts are, then funny things can happen. The experience doesn't feel quite right. And so how we combine those together, that's sort of the sensory compliance needs to come together so it's synced together both in time and space. That's on the bottom here, I have multimodal. That's what I mean by combining those different senses together instead of thinking about them in isolation. In balance and physical motion, some people classify that underneath proprioception, but it's primarily the inner ear that gives you that sense of knowing if you're going to fall over or not. And so as I lean around, I can kind of keep my balance. And that's something we also take for granted, and without that, we would fall over pretty quick. And then there's the physical touch, things that are pushing up against our skin, our muscles and such. That is what we'll be talking about today throughout most of the talk. And then smell and taste, of course, those are important in the real world. Pretty difficult to do in virtual reality. There are researchers definitely focusing on that, but there's a way to go before we can make that sort of, a robust and consistent experience. Going back to the earlier days of virtual reality, back in the late 90s and early 2000s at UNC Chapel Hill, we had something called the pit demo. Essentially, we'd have users come in, put on the headset, and interact in a physical space. They could reach out, they could touch cabinets, they could put their hand up against a window. We had a simple fan blowing against through that space, so it felt like there was a breeze coming through the window. They could pick up a ball, they could drop it on a target, etc. And then after they got comfortable, what we did is we opened the virtual door. They'd physically walk into the next room, and there'd be a big hole in the room, something they were not expecting. And at that point, we'd take physiological measures to see what would happen. And we play with different conditions to see if there'd be much of an effect on heart rate and such. And so we had something we called the diving board. Basically, you could walk out over the pit onto the ledge. And one thing we did, shown in this picture here, is we had about 1.5 inches thick piece of plywood that you'd feel with the bottom of your feet. You'd feel over that ledge as you look down over that ledge. And that was a pretty surreal experience to be able to feel that height. And I think that's one of the reasons why this in its day was kind of considered one of the best VR demos there was. There was Jaron Lanier, who coined the term virtual reality. He said, this is what I always thought it would be like. Even though he coined that term, he hadn't really experienced the full potential that he thought virtual reality could be, and this is what he kind of dreamed it would be. Then Randy Posh of the famous lecture, or famous for his last lecture, he said there is this VR demo, and then there are all others. And I think a huge part of that was because of the physicality. We're doing some other interesting things as well, but I think that was really what made this compelling. Today's consumer VR is done extremely well. I'm very happy where the technology is today, that you can go down and buy it at consumer level prices. However, in most cases, these virtual reality systems do not convey physical touch, right? They might have the controllers, but if I reach out and my hand goes through an object or a wall that I expect to be there, we have that break in presence that, oh, okay, maybe this is not real, even though you believed it up to that point. So these consumer systems, they're targeting a mass audience, not specific use cases, where you really want to get into a subject and get subject matter experts involved and such to get the real element of the physical equipment, for example, that someone might be using. In fact, if you're using virtual reality for training, there's a danger of negative training transfer. That is, if you train, if I'm fumbling with if I'm using a virtual device, then I go out into the real world and I attempt to use a similar device, but it's physical, I'm probably going to be fumbling around with the device. In some cases, bad training can be worse than no training if you're going to mistrain. So we need to be very careful of that. And also, more on the simulation versus the training side, is that when we prototype new equipment, that's a very long process. And to be able to test it, of course, you build the thing and you try it out and such, but typically that's done in a laboratory setting. It's not done in the context that you would actually be using that. And that's especially important for some industries. We're working with first responders where they are operating in dangerous incidents that they don't experience very often. They don't have that opportunity until something really bad happens. And so with virtual reality, we can do those things, and specifically when we integrate physical equipment, it can be a good fit. And so as far as the fidelity of these experiences, Ivan Sutherland said back in 1965, he really created one of the first virtual reality systems. He said the ultimate display would, of course, be a room within which the computer can control the existence of matter. That's we're not quite there yet. A chair displayed in such a room would be good enough to sit on. Handcuffs displayed in such a room would be confining, and a bullet displayed in such a room would be fatal. So I don't think we want to go that far with matching the physical, fidelity of, actually dying from a physical bullet. But the point here is there's a whole lot to do, and it's not just the visual and the audio components of the system. So here we break it down into representational fidelity, experiential fidelity, and interaction fidelity. So representational fidelity, that's the degree to which the experience, the way it's designed, conveys a place that is or could be on Earth. That is, doesn't match real life, versus a game may not. It may be more of a cartoon world, and that's okay. It depends on what you're trying to shoot for. And so it's not higher fidelity is not necessarily better in a lot of cases, right? If you're going for a sort of abstract, relaxing world, maybe you want it completely different. And so these are, spectrums to choose your design space. Experiential fidelity, in a similar manner, that is, does that experience match what the designer intended? And so it's something that's a linear experience can have higher experiential fidelity because it's sort of always consistent. If you go repeat that experience or someone else that tries it, it's really going to be that same sort of experience. So 360 film, for example, has high experiential fidelity, versus if it's a free roaming world, then lower experiential fidelity. Then interaction fidelity. So that is the degree to which physical actions for a virtual task correspond to physical actions for the equivalent real world task. Am I interacting in the same way that I would interact in the real world? And so on the sort of on the far left of that spectrum are these easy to use interfaces. I can look off on the object and off in the world and say select. That's not how you do it in the real world. But then on the extreme opposite of that is the actual physical grab or having physical props in the environment. And so somewhere in between there, it feels like magic, right? If you're going to throw fireballs from your hand, you're sort of doing physical actions, and it's sort of, it seems like it could be feasible in some way, but not how the world actually works. So here we're focusing on the far right of that physical high interaction fidelity with the physical props. Okay, so interaction fidelity as far as how you interact with the system. You can have buttons, you can have speech recognition, you can have that, the realistic grabbing out in the world, with the magic somewhere in the middle of those superhuman powers. And then how do we interact? Well, there's a pretty important input device that I believe is pretty much the most important device, whether it's within virtual reality or some other advanced system. Fortunately, this has been around quite a while, and it works exceptionally well. It's figured out pretty well, and that's called the human hands. So a large proportion of our sensory and motor cortex are devoted to the hands, and hand tracking technology is just the mediator that brings the hands into the system, into the simulation. And here's just listed kind of a conceptually of what parts of the brain are devoted. You can see it's a good part of the brain are devoted to the motor cortex and the sensory cortex. And these sort of cartoon characters represent how much approximately portion of the brain is devoted for that. So you can see the hand and the face, interestingly, those are quite large on both the motor side and the sensory side. An example of how if you don't get something right, it can feel a little bit awkward. So if you hold your hands out in front of you, simple exercise here, and you just close your hands together, you're kind of used to doing that, right? It feels comfortable. But then take your hands, uncross them, and moving up a little bit, and cross your thumbs over in the opposite way, so the other thumb is on top of the thumb that would normally be on top. And that feels a little bit awkward. It doesn't quite feel right. So even with that very subtle change, it's a different type of experience. And so the point here is that these very subtle ways of how you move your fingers and such can make a huge difference. And that's sort of the challenge of building a intuitive, comfortable experience within virtual reality. Just even these minor changes can make the difference between kind of feeling funny versus feeling intuitive and natural. Now controllers, they work really well. I'm a big fan for a lot of use cases. It pretty comes standard with virtual reality systems. It's a really good fit. In other cases, you may not want to have the controllers. If you want to have your hands free, for example, maybe you want to reach out and interact just in free form, in midair. There's challenges with that as well. And so here's sort of the pros and cons of each. The controllers are pretty highly reliable. When you push that button, it's pretty much going to know that it got the button 99.99% of the time. You can add haptics, that sense that you can add some rumble to the controller, and appropriate for a lot of tasks. Bare hands, on the other hand, allow you to interact with physical objects. So if I want to pick up a prop, I can pick up that prop without having to set down the controller. It can become computationally intense, sure, but processing power is becoming better. The bigger challenges are the laws of physics, right? If I reach my hand in front of a physical prop so that the sensor is no longer seeing the hand, you don't know what the hand's doing. As well as lighting conditions. If it's not great lighting conditions, then it can be more difficult to track. Now, there's also the sensing technology of what is the user intending to do, right? With buttons, it's sort of this binary on or off, and it's the user knows when that button's pressed down or not, and the system knows if it's pressed down or not. However, when you're trying to infer human intent from body language, as humans, we can't do that well because there is not necessarily a truth, right? You're kind of reaching out without actually, in some cases, intending one thing or another. So we don't know. It depends upon the context. It depends, what's going on in the user's brain, and so you can't get that right 100% of the time, even with infinite processing. So what should we use? Should we use controllers or bare hands? Well, one answer that as many will if you've read my book or heard my other talks, is that the answer, of course, is it depends. Right? The answer we don't like, but the answer I like to give. And it does. It depends on your use case. It depends on your users. It depends on a whole lot of factors. But another answer is, why not both? Right? Why have to choose one or the other? And so in our case, for some use cases, not all use cases. So if you have physical props, you can use both. And so we use the Leap Motion, right, to sense where the hands are, and then we use Steam VR tracking, and we sort of had this hybrid system of mixing those together. So if I'm not picking up the prop, then I can do whatever I want with my hands. I don't have my hands free to do what I need to do. And then if I want to pick up a physical prop, then I can track that in the world as well. Now the challenge is calibrating those together so that they agree with each other in space. You don't want the system thinking your hand's over here, touching a physical prop, and the system thinks the prop's 6 inches to the left of your hand. There's challenges when you pick up that prop. Then Leap Motion wasn't designed to work with physical objects. That's just not what it's designed for. And so we've gotten creative. For example, when your hand gets near a prop, then we can snap the hand to an approximate location where the hand you would normally grab that object. We also can interpolate in different ways and do some sort of creative ways of perceptual hacks, I guess you would call them, of adding constraints so your hand slides there along a bar, for example. So there are some things we can do there, but you really have to get creative with those approaches. Now, as far as the best use cases for virtual reality, I mentioned we're working with first responders. Here's a case of hazmat workers attempting to repair a leak. And so when there's interaction with physical equipment, obviously if we're doing physical VR, it makes sense that the use case has some physicality to it. Now, that doesn't mean that VR with physical props is the answer in all situations, right? If you just you have a drill or you have a wrench, you don't need virtual reality for that, right? Just give the guy a wrench and say, go practice doing this. But if it's more complicated than that, or you have you want to simulate dangerous conditions, for example, that can be pretty difficult to do in the real world, such as gases or fire, for example. You can do that in the real world. Firefighters do have burn sites, but they may only be able to experience that maybe once or twice a year in training when they're trying to learn certain things. Obviously, in the field, when they go onto these incidents, they will experience those, but in some cases, some of those things can be pretty rare. So that leads to the focus on high-risk, low-frequency incidents. If you're doing this job every single day, you don't need to necessarily practice it within virtual reality. You get that real-life experience. But in hazmat cases, there's the use of certain tools and such that might only happen once or twice a year, or even less. It may never happen. And so how do you prepare for those? You've only had it in you can do live action training, but some things you can't do in live action training. For example, we have I'll be showing an air monitor here in a moment that there just isn't a good way to train for it in the real world. And so industries that fit these are, I mentioned, we're working with public safety, but also the military, the nuclear industry, oil and gas industry, and space operations are, I think, a really good fit for, going beyond just the consumer VR systems where you need to focus on very specific use cases that fulfill those criteria up above. Okay, so here's the air monitor I mentioned. So this is a real-world air monitor here on the left that gives different parts per million of different gases. And so this was not our idea. We only, realized this was a good fit by talking with subject matter experts, with hazmat specialists. So hazmat training, using one of these devices is typically done in a lecture format, similar to this video here, having a PowerPoint slide of sitting in a classroom. Visual audio, right? And they might have some video or something, but typically not. And so they're just passively observing something. And maybe they'll, they pick up the device and look at it, but there's not necessarily good ways to simulate those readings on the device in the real world. In fact, how it typically happens is the trainer, when you're actually doing live action training, the trainer says, well, this gas is at this level. And he essentially is giving away the answer, right? So that draws attention to the air monitor. giving away the answer, and also detracts or adds to situational awareness that they probably wouldn't have in the real world. If you're distracted by some craziness, some danger out in the world, you might forget about the air monitor. But the trainer is essentially telling them what to do, and so it's not necessarily realistic of how they actually need to perform and behave under very different conditions in the real world. And so that experience is only gained from those rare and dangerous real world incidents that happen very rarely. So these air monitors are available pretty much on every fire truck, but typically only utilized by hazmat specialists. And so a lot of times they just need to take this device. They could go measure the gases themselves, but they call in the hazmat team that can take time to arrive and such, and that can add 20 minutes when minutes matter in these situations, because they're not confident in using that, because they've only tried it a couple times live action training, or maybe they tried it they watched it in a lecture, and they're probably not going to remember that in detail, or be confident at least to be able to use it. So we started designing a physical prop. Here's some very early sketches of that. And there it is in a CAD program, and that's actually a rendering, but it's essentially a rendering of what the 3D print looks like. And there's one of the 3D prints with all of the sensors inside. So those are Steam VR sensors with essentially little photodiodes that look at the lighthouses sensors out in the world, and so that it's able to know where the object is in space. And there's the final, or I shouldn't say final, a version, because we're constantly iterating upon this. We actually took the cover of a real air monitor, designed it to fit inside that, and then we put that on there so it feels like the same material, the same thing that they would have for the real piece of equipment. And so here's an example of a user physically interacting with that air monitor, and down on the bottom left is what the person sees in the head-mounted display. And then we can take that and put it into context of actually being at a scene of an incident, going out and taking gas readings out in the dangerous situation. So here's a video of a hazmat experience, and the air monitor is an important part of this. So we have a leap motion hand on the front here. Apologize, this is not playing. There we go. Okay, so in that case, we are using that virtual interaction. We don't need a physical prop there. It's a big button, and it works pretty well.
Let's go. Go ahead and grab your air monitor. Turn it on by pressing the red power button on the right. Once that powers up, you'll see 4 sensors on the screen. And I'm sure you know those are oxygen, LEL, CO, and H2S. Go ahead and do a quick pump test by putting the meter up to the test attached to that cylinder. It's filled with the calibration gas for all 4 of our sensors.
Notice the air monitor just physically touching the Pelican case, so you actually feel it pushing up against something.
Jump on the back and head out.
So we are only physically representing what the user is going to actually touch. And we got them through that experience so that they're not going to walk off into the distance. Now you can see here, this is just a very simple physical bench, but that's all we need to do, right? We're very careful with the narrative to get the person to go in specific directions, versus if it was a free roaming world, that would be a problem. We also added vibro-tactile feedback to the seat, so it rumbles when the vehicle starts moving, and that adds a huge amount to that sense of, oh, I'm actually moving, even though you're not actually moving. And we believe, based on anecdotally, that this seems to reduce motion sickness. So we haven't done a formal study on that, but that's what we want to do to see if that is actually the case by providing that vibration, does that disrupt the vestibular system, the inner ear, so that you feel like that. So that continues on, goes out into the site and measures some gases and such. Okay, so there's different ways to think about haptics, right? So far we've been just saying physical props. Okay, but there's more to it. Different ways, different approaches to add haptics, or the simulation of physicality in virtual reality. So in the academic world, there's something called passive haptics, and basically all that is something that it's not controlled by the computer. It can just be essentially a physical prop. It's not going to vibrate. It's just going to be, it might be tracked, but it's really not doing anything controlled by the computer. Versus active haptics is something that the computer does control. So for example, vibrating the controller or the track device, or physically pushing up against you so you feel some physical resistance. And then the prop can be tracked or non-tracked. So you don't necessarily need to track everything. For example, that bench, we carefully calibrate it so that it's in the spot that it's supposed to be, and it's not going to move, so we don't need to track it. We don't need to track everything. And then is it fixed in the world, or does it travel with the user? Is it held or is it worn? So for example, there's haptic, vibrotactile belts that you can use to kind of give you a sense of direction around the waist. You don't necessarily need to track that. Or if you wanted to say push a button, push to talk, you could have that here. You could have rings on the finger. You could have whatever you need. In some of those cases, you might want to track it. In some cases, you might not want to track it. They might also, some might be passive, and some might be active. And then how do we bring all these together? So, similar to what I was saying earlier about the different sensory modalities coming together, here we got to make sure they're synced up in time and space. If you reach out and see something here, but it's really physically over there, then it's going to be pretty confusing to the user. And so we thought about these different levels of physical VR, right? So tier 0 would be, standard VR. It's got controllers, or maybe it's got leap motion, but we're not adding physicality to it beyond, the straightforward, standard system. And so tier 1 is just doing something simple. If we're going to lean up against a wall, then you have a physical wall there. Then we can add tracking as well onto the props, and that's if the thing's going to move. And then we can also add buttons. So for example, the air monitor that we showed, that has buttons on top of that. Or adding buttons onto the existing equipment. So I should back up here. The air monitor is actually tier 5. Yes, it has buttons, but it was also custom designed and built. Tier 4 is also having other input and output. For example, we're going to be showing something with a trackpad on the prop later on, or the active haptics providing output. Then tier 5 is something that you have full control over the prop. You're adding electronics. You're doing more than just adding on tracking and adding buttons and such. And so now we'll show some examples of those. So the air monitor you saw, that was tier 5. Down at the bottom left, custom designed and built. Now the advantage of that is if you're building a new device, then you don't want to necessarily just bring in existing equipment. You'll want to be able to say, oh, what if we move this button over here? What if we try this new interface, or it has different ergonomics, a different feel to it? You have complete design over everything. So that's sort of, it takes more to do, but you have a lot more control and ability to change things up. If you want to reuse existing equipment, you can just add a sensor, this being the HTC Vive Puck, added onto the existing piece of equipment. So this is a real air monitor here. And for button inputs, we simply overlaid our buttons onto the existing buttons. Instead of cracking the thing open and destroying the thing and having to reverse engineer it, we just place the buttons on top of the existing buttons so they're in the same place. They feel, pretty close to being the same as the buttons they're used to, and, it's pretty straightforward to do. So that's an example of tier 3, because we added the tracking and we added the buttons. An example of a tier 1, and these don't need to be, high quality, expensive things. They can be, pretty easy to bring in some cases. So in this case, we're simulating a basic vehicle search, and we just went to the junkyard and ripped out the back trunk of a car, then set that up in our office. And then, so that doesn't need to be tracked. Although we do track, you can actually see up here on the upper left here, there is a vibe puck. We use that for calibration, but then we turn it off just because once it's set, there's no need to track that. And then the wheel well cover, right, you can lift that up. This is a simple representation of the leap motion hand there. You can reach out, lift that up, look underneath. And in that case, we do need to track it because we need to know where it is in space. So that would be tier 2. Very straightforward. Now, something a little bit more complicated is doing more and adding more components, and so mixing the tiers together. And so this is a fire truck pump panel simulator, right, where you set the water pressure and such on the side of a fire truck. It goes through the water hose. And on the left, you can see the real-world device we built. We added, this was done for a contest for the IEEE Virtual Reality Conference couple years ago, and we added different buttons. We added, a pull lever. We added a dial. We added some, simple tier 2 in this area, right? We just added a pup on top of a pipe, right, that you insert into another part of the system. And so we're essentially exploring the use of these different props and these different input components. So that was just done with standard Arduino components and such. Now, again, it doesn't need to, look super, it doesn't need to be, a perfect product, right? Doesn't need to be super high fidelity in the physical world because they're not going to be seeing it. They're just going to be touching it. But then within virtual reality, we can do different things. We can add different monitors. We can, add more detail and, something that's a little bit more compelling, and also change things up. We add components to it that maybe don't even exist in the real world if they're not going to be likely to touch those things. And then, so this is just in our virtual office here, but we can also put that in, a very different visual element of putting it on the side of a fire truck. Now, obviously, we don't want to physically model an entire fire truck. We just need, again, physically build what the user is going to touch. So only this area is physically in the simulation, and everything else is purely virtual. Here's another example of a tier 5. We're exploring the use of an Armband interface. And so this has a trackpad on top, and there's a couple points to this. One is that in some use cases, in this case we're exploring triage, recording a triage in a mass casualty situation. In some cases, your hands need to be free. You don't have to pick up a controller, set it down. And so here, it's a worn device that always travels with you. And it's tracked, so you can look and you can interact with it. But not necessarily have to look at it. Once you get good with an interface like this, for first responders, we believe this can be important, that you don't want to always be looking up and down, right? For situational awareness, you may need to be paying attention to some danger off in the distance that you don't want to be looking back and forth. So the advantage here is once you get good at it, then we believe that's going to be valuable, because now I can do input and record information without necessarily having to look at that information, right? You go by feel. So we're exploring with adding different physical cues onto this device so you can better feel what it will look like. But you can look at it if you want. So there will be a virtual screen on this for that provides information. So in some cases, when you do need information conveyed, then it would be there. And in this case, this is simulation of creating a new product, not necessarily training, but more, okay, if we were going to build this and actually put it in the field, let's figure it out, what the user, the UX and the design and the processes that go along, what are the processes the person needs to do in order to, use it effectively and add value to, the bad situations that first responders find themselves in. How can we do that before building the actual thing? And even if you do build the actual thing, it's pretty difficult to replicate that in the actual dangerous situations. Again, you can do live action training, but live action training doesn't have all the context. So a lot of value here of being able to build new products. Maybe it's this, maybe it's something entirely different, but to be able to simulate and to inform the design of the real world device that may have nothing to do with virtual or augmented reality. So essentially using this as a design tool. Okay, what we also sort of noticed is that users seem to be, after they reach out and touch a few things in the environment, that users become much more trusting. If any of you have, watch people do virtual reality when they first put on the headset, they're sort of, not sure of themselves, like, am I going to run into a wall? Or, their steps are very, very slow. And so what we found, if they reach out and they start touching just a few very basic things, they start trusting the simulation as if it's more real, and thus they're more confident and they walk more quickly, right? There's a little bit of danger there, because if you don't have the room set up in that, they might run into the wall that's not supposed to be there. So you need to make sure that you have everything calibrated well and such. But once they do trust that, they'll just walk across the room, pretty briskly like they do in real life. And so the research questions we have is, does having that physicality result in faster walking towards objectives, right? It's a pretty simple measure to start with, just, time to completion. And then does adding physicality to VR result in more closely matching real world performance? So not necessarily better performance, but no, matching real world performance. For in VR, you can push a button and magically have the solution, and that might be faster in the real world, but we're not trying to train for pushing a magic button. We're trying to train for the real world. So if they're slower in the real world, we want them to be slower in VR as well. And so ongoing user study had been put on hold a little bit because of the coronavirus, but getting started up on that again real soon now. The research question again is, specifically, does adding passive haptics result in better matching to real world tasks? Starting with the simple, very simple, which is time to completion. And so the hypothesis is adding the physical props, so comparing VR with physicality compared to standard VR, does the condition with physical props, does that result in task performance that more closely matches the real world? And sorry, 3 conditions again, listed here on the bottom. And so we built our virtual space to match our physical space. And so the idea is, if you're going to go through the environment, we're going to measure them with real world performance without virtual reality rendering at all. We actually are going to put a head mount on them so that that weight and such is the same in the real world, and also use that to track the user, because we want to track both in VR and real world, but trying to match up those conditions so that the real is reasonably close to the virtual, so that we can do a fair comparison. And so the idea here is, you need to walk across the room, and if there's physical objects in the way, do they behave differently when there's physical objects? And I think the obvious answer is, yeah, probably so. But then we can start looking at more, if that's the case, right? Start with that base case, then start looking at more interesting conditions and such to see, what factors contribute to better matching to the real world. And then once we find that, that will lead to, okay, now we have a pretty good, we're pretty confident that it's closer matching to the real world. Then we can start adding those dangerous elements to be able to train for those dangerous incidents. Okay, so we believe this is going to have significant impact further out in the future. As we mentioned, a couple examples: improved not just is it better VR and is it better training, but evaluation of those interfaces, the processes, and usage, and to be able to iterate upon those things, right? Because even if it's a straightforward thing that already exists in the world, it can be difficult to create better processes, because you can't necessarily get a sense or of how the person's going to behave under that dangerous situation, right? If they're nervous, or if they're all suited up, they might be behaving very differently than they would in a laboratory. Okay, we also believe in some cases this having physicality will decrease cognitive load, because you can go by feel, right? You can feel the interface instead of having to look at the interface and process it visually. And of course, I think the very clear benefit here will be better training transfer to real world incidents, specifically when they're using physical equipment. Not trying to replace all equipment or all training, but where is it of the most benefit? So again, if they need to pick up a wrench and tighten something, then okay, maybe you don't need virtual reality for that. But the right use cases, we believe that will have significant impact of having better prepared workers. Better design tools, similar to the first point there of, okay, now we can change up, we can 3D print the tools, and add sensors on them, then change them up, right? Provide better ergonomics and, evaluate those more quickly than we can be able, do in the actual, the full product. And this ultimately will lead to faster responses for critical incidents. Okay. That's my presentation. I'd love to discuss this more with anyone here in the audience. Just reach out to me at jason@nextgeninteractions.com.